Hi, hello again, everyone. This is part 2 of your vector analysis lecture in Tripoli 23. And let's pick up where we left off from your vector field, definition of your vectors in the Cartesian plane, unit vectors, the norm, etc., etc. Let's now move on to uh, some could say that this is your vector multiplication. So, so let me just try to write that. So vector multiplication. So let's put it in quote and quote. So one way to multiply vectors is actually using dot or the scalar product. So by definition, for an n-dimensional space, the dot product of two vectors, A and B, which are defined by their n components, right here, is this formula right here. Sorry about that. Let me just fix that. There you go. So this is defined by this equation. So don't be worried by the length of this equation right here. Basically, it just says that you just need to multiply each component by the corresponding component of the other vector, and you add the products of the the products of each component. And actually, it's related to the norms of A and B by this equation, and theta is the angle between the two vectors. So the maximum value of your dot product actually is when theta is equal to 0, or what does that mean? When your two vectors are aligned with each other. So let's say this is vector B, the smaller one, and vector A, the bigger one. So your dot product is at its maximum value when the vectors are aligned. And it's at the minimum value if the vectors are not aligned together or 180 degrees apart. Okay? Alright. So the properties of your dot product is that it's commutative. It doesn't matter which one goes first. Multiplication of each component is commutative. So you'll see that. So multiplication of each component is commutative. You'll see that if you just flip the order of the operands, you'll get the same result. It's distributive over the sum of vectors or vector addition. And when you have orthogonal vectors or vectors that form 90 degrees, uh, 90 degree angles, which is cosine 90, you'll get 0. So cosine, it makes sense with the formula because cosine 90 is 0. So orthogonal vectors have a dot product of 0. Okay? So an interpretation of using the dot product actually is when we make a projection of the vector on one direction. For example, if we if we get the dot product of A and B, we get the apparent length of A on the direction of B, or on the component of A that is on the direction of B. So recall that for each vector, it has components. And by convenience, we actually express the components, or we require, we require the components to be orthogonal to each other or 90 degrees with each other. So in this case, A has a component on B, which is the result of the dot product of A to B. And the other, the one left out, is actually a component that is orthogonal to B. So which kind of makes sense. Okay, so let's write A as some value which is on the direction of B plus some value that is normal or orthogonal to the direction of B. So let's say this is x AB and y AN. So if we get the dot product of A and B, so let me just put there. So if you get the dot product of A and B, there you go. The result would be x AB dotted to B, there you go, since this component of A is aligned with B, there you go. That's your component. You'll get the value here would be equal to x times the component of B along B. Okay? So something like this. And the dot of your normal component to B by B, well, if it's normal, then the dot product of this will just disappear in the operation. Okay? So, you can think of the dot product as some kind of apparent length that A projects on B. So if you look at this side, these are your eyes from here. Sorry, I'm not a good painter. I'm not good at drawing. So just imagine these are your eyes. Okay, so if you look towards this direction, you just see one line, which is B. A makes A makes an apparent length from your point of view, and that is the projection of A on B. Okay, so that can be computed using this formula. So that's A dotted to B divided by the norm of B. So notice this term right here, B divided by the norm of B. This is actually the same as getting the dot product of A on the unit vector on the direction of B. And that is the scalar projection of your vector A on the direction of B. The vector projection is different. You just need to add that direction by your scalar projection. So scalar projection means the value is scalar, as by definition of your dot product. Vector projection, you just need to add that direction. So which makes sense, since if it's a projection on B, then it should have the same direction with your vector B. So that's your physical interpretation of the dot product. And this is an important concept when you're transforming your Cartesian coordinate system, which is based on a rectangular prism, to your cylindrical and your spherical coordinate system, which are based on a cylinder and a sphere, respectively. Okay, so now let's look at the other type of your uh, quote-unquote vector multiplication. It's the cross product or the vector product. The definition is the cross product A cross B is defined as vector C that is perpendicular to both A and B with the direction given by the right hand rule and the magnitude equal to the area of the parallelogram that the vectors span. Okay? Basically, if you want to get the area of a parallelogram defined by A and B, so let's go back. Something like this. Okay. So if you want to get the area of this parallelogram, you just need to get the magnitude of the cross product between A and B. So actually, when you get the cross product between two lengths, you actually get the area between them. So this will be an important concept when we talk about surface areas. But let's leave it at that for now. Cross product defines an area. So if your dot product defines a projection, cross product defines an area. And A cross B is defined by this formula right here. The inside is defined by sine theta instead of cosine theta. And this A sub n is a normal vector, normal unit vector, perpendicular to A and B. So the properties of this is that it's anti-commutative. If you reverse the order of operands, you'll get the negative of the intended result. Also, it can be distributed to a vector addition, like so. So how do you calculate then this cross or vector product? How do you know where AN is in the first place? So this is just a formula. The magnitude is just a formula. AN, different story. So you can actually, well, let's go look at that later. This is the physical part of that, physical interpretation of your cross product. If you put your first operand on your pointing finger and your second operand on your middle finger, then the thumb corresponds to the direction of their cross product. So again, the magnitude of the area between the parallelogram of A and B is defined by the cross product A cross B. And the normal vector, again, defined by the right-hand rule. So to compute that, so given you have A defined by its components, AX, AY, and AZ, and B also defined by its components, BX, BY, and BZ, you can get the cross product by getting the determinant of a 3 by 3 matrix defined by your unit vectors of the Cartesian plane and the unit vectors of, the component vectors, component scalars of your uh, vectors. Okay. So how do you get the uh, determinant of this matrix right here? Quite simply, you just need to get the diagonals. So you multiply the diagonals together. In this direction, it's positive. And on the opposite direction, right here, it's negative. So you have to extend your matrix here in this part. So you put this part of the matrix. So let's go back to, let us delete all that. So you just need to copy this part of the matrix to this side, and then you group your operands, and you'll get this expression right here. You'll simplify your expression with this. So that is the cross product. As you can see, it's already in vector form. So just a note, you can see that this is a 3 by 3 matrix defined on a cross product. That is because this cross product only applies to 2 and 3 dimensional three dimensional spaces. It's a special type of matrix, or it's a special type of vector multiplication only defined for the 2D and 3D space. Okay, so example, we have M and N. Get the cross product. Well, first you need to put the unit vectors in the first row. M, since M was first, you need to put the components on the second row of M. Okay, so the second row. And finally, N, 1, negative 2, 0, 0, since you can actually extend this to 0, A, Z. There you go. So now you can get the determinant of this matrix right here. You can use this definition and you'll get this expression right here. There you go. Okay, so that's how you solve cross products. So now let's move on to other coordinate systems derived from your different shapes. Recall that your Cartesian coordinate system for 2D is defined by the square. Interesting properties of the square is that the x and y coordinates are perpendicular to each other, and that's also the basis of other coordinate systems. So let's convert this square-based coordinate system into a polar coordinate system. So in the polar coordinate system, we have new unit vectors defined. If the unit vector for your Cartesian coordinate system is x hat, so here to here, and y hat for here to here, your polar coordinate system is defined by rho hat and phi hat. Rho hat is the direction of the vector that is radially outward from a circle along the xy plane. Radially outward. So if you have a rho that is defined by this vector right here, then the value of rho, or the vector rho hat, actually changes. so is the vector phi hat, which is instead of radially outward, it's tangent to the circle, and it rotates counterclockwise. So at this point, your rho hat points tangent to the circle and points downwards. Okay, so it's always perpendicular to your rho hat. That makes rho hat and phi hat viable component vectors for a vector defined in this polar coordinate system. So how do you relate the Cartesian coordinate system to the polar coordinate system? So to relate them, well, actually, if you have the same vector or that's originating from the origin, this vector has length rho. Okay? And the angle between the x-axis and that vector, that is your value of your phi. So notice that they create a triangle right here. So again, I'm sorry for the crappy drawing. I'm not really good at this, but I'll try my best. So they form a triangle right here and here. There you go. So they form a triangle. The length of this is y. The length of this is x. So they form a right triangle since y and x are always perpendicular. Then you can solve for phi and rho in terms of y and x. So by Pythagorean theorem, rho squared is equal to x squared plus y squared, and you'll get this equation right here. Phi is just, the tangent of phi is opposite over adjacent, which is y over x. So you get the tangent inverse of that, you'll get phi. If you want to convert this to your Cartesian coordinate system, you'll just use trigonometry. So again, SOHCAHTOA, phi, or the cosine of phi, is defined as the adjacent, which is x, divided by the hypotenuse, which is rho. And you'll get this equation here to convert your polar coordinates back to Cartesian coordinates, and also true with your y component. Okay, so let's expand this polar coordinate system. So instead of a rectangular prism-based coordinate system, we can look at something that is based on a cylinder. So what use is this? Well, it actually kind of simplifies other physical uh, objects that cannot be easily described by a box. For example, curves. So a lot of conductors are actually cylinders. And to analyze the fields in these conductors, we need to have a certain symmetry in our coordinate system. And the chosen coordinate system for that is a cylinder, which makes sense since a lot of these conductors are actually cylinders. Okay, so now the cylindrical coordinate system is defined by a point rho, phi, and z. Okay, so instead of x, y, z, it's rho, phi, and z. So the conversion from your Cartesian to your cylindrical is kind of similar to your 2D Cartesian and your polar coordinate system. Okay, so with this also is a new set of unit vectors, rho hat, phi hat, z hat. Or so in Triple 23 we'll use a rho, a phi, and a z. Okay, so again, rho hat is radially outward the cylinder. So if this is the radius of the cylinder defined by rho, rho hat is radially outward that direction. And phi hat is again always tangential and moving away from the x-axis or rotating away from the x-axis like this one. So if you're looking at this point right here, so let's use a new color for that. So if you're working at this point, this is the radius of that cylinder. Okay, and rho hat would be pointing outwards. Phi hat would be from x going to y, so this would be phi hat, and z always still the same, pointing upwards like this one right here, z hat. So that's the relationship between your unit vectors with the point in space. So as you've noticed, at each point in space, actually, your A raw and A phi changes its direction. That means if they are in an integral, let's say, an integral with A raw across different values of your uh, phi, let's say, A raw changes direction. So you can easily take it out of integral, uh, your integral, your integral operator. Okay. So as compared to your ax, ay, and az, your ax, ay, and az at any point in space, they're still the same in direction. Still the same. If you're here, it's still the same. So if it's in an integral operator, you can actually factor it out. Direction does not change. Okay, so just some note: A raw cross A phi is equal to AZ. So by the definitions, when you get the cross product, you'll use this, point this on your pointing finger, point this on your middle finger, and where the thumb points, that's your Z direction. Okay. So how do we convert your Cartesian to your cylindrical coordinates? Well, you just need to convert your x and y to polar coordinates, then retain z, since it's just the same z right here. So what just changed is that your x and y became raw and phi. So something like this. Okay, so when we're talking about vectors instead of points, so when this is just a point in space, if we're talking about vectors, so given a vector A in a coordinate system, let's say Cartesian, we can transform it to another coordinate system, let's say cylindrical, by projecting it to the desired coordinate system. So given a vector A with AX, AY, and AZ components, so it's in Cartesian coordinates, we want to convert it to cylindrical coordinates. So the first step is to solve the component of your cylindrical coordinate version. The components would be your A raw, A phi, and AZ. So again, your A raw points radially outward, phi points tangential, perpendicular to your radius, and it's flowing counterclockwise. And finally, your Z points upward. So you just need to, how do you get the component of this vector A in cylindrical coordinates? Well, basically, you just need to you take the dot product between A and the unit vector along that direction. If you want to get the raw component, well, you just need to get the dot product of A and A raw. So let's try to do that. So A raw, which is equal to A dot A raw, and you'll get this expression for A dotted to A raw. Then by definition or by properties of your dot product, you can distribute that across each term. Okay, and you'll get these expressions right here. There you go. So same is true with A phi and AZ. You just need to get the dot product. Just need to distribute it along them. Same here. Okay. So how do you get then the values of these dot products right here? So you'll get them from the figure actually. And well, this is the table that summarizes the dot products. You don't need to memorize this. You can actually derive it from the definitions. So let's go back to this um, illustration right here. Or quite easier, let's look at this illustration right here. Okay, so this is your raw direction. This is your x direction, and this is your y direction. Take note that they have a magnitude of 1. If you want to get raw dotted to x, so that's raw hat dotted to x, that is equal to the magnitude of raw times the magnitude of x times cosine of the angle between them. What's the angle between them? That's phi. So that's the cosine of phi. Okay? So let me clean that up. I'll use a better way, a better application instead of drawing. Okay, so we have raw. Okay, so A raw. Okay, dotted to AX. So as we know from the figure, the angle between raw and X is phi. So this is equal to the magnitude of A raw. Okay, so let me just, where is it again? Oh, there you go. So that's the magnitude or the norm of A raw multiplied by the magnitude of AX times cosine of the angle between them, which is phi. And the magnitude of both AX and A raw is 1, therefore the result of the dot product is cosine phi. There you go. Now you can actually do the same when deriving A raw dotted to AY. But in this case, the angle between them is different. So the angle between A raw and A phi is, since Y and X has a 90-degree angle, then this angle between A raw and AY is equal to 90 minus phi. There you go. So that's 90 minus phi. Just need to substitute it here and use the double angle formula. Sorry, the sum or difference of angles formula, and you'll arrive with sine phi. And finally, you have A raw dotted to AZ. Since they are perpendicular to each other, right here, raw and Z, their dot product is 0. Now you can do the same when you want to project them to phi hat. So you can do the same method. Just need to get the angle between them. You just need to solve the angle between them based on the relationships or the definitions of your unit vectors. So I won't show it here. You can do it now. So let's proceed. So since this is the summary of the dot products, so you substitute ax dot arrow to cosine phi, ay dot arrow to sine phi, ax dot a phi to negative sine phi, ay dotted to a phi by cosine phi, and az, well, it has a mind of its own. It's not related to any of them at all. And finally, the final step, for each of the components of your cylindrical coordinate definition, you just need to substitute these values to your variables. So, an example, you have a field F defined by this equation right here. Want it to be in cylindrical coordinates. Then first is you project it to the each of the unit vectors of the cylindrical coordinates. So just need to dot that. Then distribute. So ax dot arrow cosine, az dot arrow 0. So you're left with this. And xyz, you need to change that with rho, phi, and z. So by definition, x is rho cosine phi, y is rho sine phi. And we have actually discussed that here. How do you derive this? Well, again, it's a triangle. Okay. Okay. So same, just substitute and simplify. Same procedure with a rho, a phi, and same procedure with az. And you just add them all up. So if this is dotted to a phi, then the a phi component is that one. So that's the a phi component. Sorry, a rho component. A phi component is this, and the z component is from here to here. Okay. So aside from having a cylinder, a sphere can also be used as a coordinate system. So what use is the sphere for us? Well, actually, the sphere is more of a convenience for higher physics. Okay? But in Triple 23, it's actually a representation of a ball of charge. Okay? So exploiting that symmetry, you can use a spherical coordinate system to easily compute for the parameters of that uh, ball of charge. Anyway, so let's look at the definition of the coordinate system. So again, it has three components. This in this case, it's now r, theta, and phi. Okay, the r hat direction is radially outward from the origin of the sphere. So it's always radially upward, so outward, sorry, from the origin of the sphere. Okay, phi hat is the same definition of phi hat from your cylindrical coordinates. Theta hat is actually the direction of the circle drawn from your north pole or Z. So if you draw a circle right here, something like this, okay, the direction of phi or theta hat is actually tangential to that circle. And it's always coming from the Z direction. Okay? And phi hat, of course, the usual. You have a circle on the XY plane. Okay, so it follows the direction from X to Y. So phi hat is tangential to that circle right there. So that's the definition of the unit vectors of your, or the component vectors of your spherical coordinate system. Okay, so r is the distance, in this case, the length of this vector. Theta is the angle between z and your vector r. And phi is the same as your cylindrical coordinate. But in this case, well, first you need to project that vector to the xy plane. So this is the projection of your vector to the xy plane. And you get the uh, angle phi between the x axis and that projection right there. Okay, so just some note, theta is bounded by 0 to pi or 0 to 180 degrees. So it's from here to here at the other side. There you go. Sorry, that's a trashy drawing. Let me repeat that. That's bounded from here to here. So let me just, there you go. Well, it's something. Okay. Phi is from negative pi to pi. So it starts from the negative x direction and bounded from here towards here. Sorry. Negative pi to pi. So it's bounded from here and goes all the way around the xy plane. Okay. So the unit vectors can be or sorry, not can be, it's actually dependent on each point in space. Again, the direction of AR is always radially outward from the origin. A theta is tangent to the sphere when you draw it from the circle when you draw it from Z. So again, this is your some vector R. There's an angle theta between them. And the direction of theta depends on that actually. It should follow the flow of theta. So something like this. Finally, A phi is just the same as your A phi from your cylindrical coordinate system. Right? So the big question is, how do we transform? So it's still the same. You can project your coordinate system, or sorry, your given vector to the components of that coordinate system. In this case, AR, A theta, and A phi. So how do you get then the dot products of each component to each other? So this is the tricky part. Okay, so to summarize that, it's these formulas. How do you get them without memorizing them? Okay, so let's go back to this definition right here. So if you're in any point in space, so let's say you're here, there's a certain distance between your point and the origin, and you can draw a vector between the origin and that point. So let's say that's vector r. Okay? So that's vector r. So to get the projection of your x direction, which is this one, here towards the x direction, so we can move it to this point, and it's still pointing towards the x direction. There you go. So you want to get your ax dotted to ar right here. So first you need to get the angle between them. That's actually hard. You can't do that by just you can do that by geometric reasoning. First thing you need to do actually is to project this vector to the xy plane first. And that kind of makes it easier. So how do you project this vector to the xy plane? Well, recall that this height right here that's your z. Okay, so this height is z. That's the height of the point from the xy plane. And this length right here is actually the same definition as your rho. How? It has an angle phi between your x-axis and that length right there. So the length of that is actually rho. And there's an angle between your vector r and theta. Sorry, vector r and your z-axis, that is theta. Then you can solve this angle right here since rho and z are always perpendicular to each other. Therefore, this vector is actually 90 degrees minus theta. Okay? So that's 90 degrees minus theta. Then you can solve for rho in terms of r, or the projection of this r hat in terms of the direction of rho hat right here. See? So you can now get the projection of r on rho hat. And from there, you can get the projection of rho hat on the x-axis. Okay? So first, you need to get the projection of r hat on rho hat. You need to get rho hat dotted to, r hat. Okay. So that is equal to the magnitude of rho times the magnitude of r hat. That's 1. Both of them are 1. 1 times 1. Times the cosine of the angle between them. So that's cosine 90 minus theta. And by using the sum of angles formula, it's cosine 90 times cosine theta plus sine 90 times sine theta, you'll get that this is equal to sine of theta. So that's the projection of rho on r hat, the scalar projection. Now we need to get ax. Okay, so since we have a projection of rho on r hat, the projection of r hat on rho hat, we can now project that rho hat direction to the x direction. So how do you do that? Well, you just basically convert rho hat to x hat using your cylindrical system. Okay? So, well, you have a length here that is equal to sine theta. You just need to know the length of this vector right here. That's the projection of r hat on x hat. Okay, so let me delete all this first. There you go. So that's the projection of r hat on x hat. Since you know this is the projection is sine theta, and you have an angle phi here. So just need to complete the triangle right here. There you go. The angle here is phi. And finally, you can get ax right here. So how do you do that? You get the dot product between ax and sine theta a rho on the rho direction. Okay? So you get the dot product of these two. You'll get what's the dot product between ax and a rho? That's cosine phi. Therefore, you'll get sine theta cosine phi. Same procedure can be done with ay. For az, well, let's go back. For az, well, again, this height is z. This angle is theta. Therefore, this angle is 90 minus theta. And this angle between your r and z is theta. Therefore, if you get the dot product between r and z, r dotted to z is equal to cosine, r hat magnitude 1, z hat magnitude 1 times cosine of the angle between them, which is theta, and you'll get this theta right here. And actually, you can do the same procedure with a theta and a phi. Okay? So knowing that a phi is perpendicular to az, well, you'll get 0 between their dot products. And finally, you need to convert AR, A theta, and A phi to the x's, y's, and z's to spherical. So these are the conversion uh, of each. The conversion of your xyz to r theta phi and vice versa. So this we have already derived this. How to get this? This is a different story. How do you get these values right here? Well, for one, the radius is r, so that would mean it's the length of this vector right here, which has an x, y, and z component. So it has an x, y, and z component defined by the coordinates of this point. Then you can get the length of this vector by just using the Pythagorean theorem. So that's the square root of x squared plus y squared plus z squared. Theta is a different story, but know that theta is equal to the angle between the z-axis and r. So you can have a line here that is parallel to this line. Okay, so that height here is the z component. So by trigonometry, the cosine of this angle is the adjacent over the hypotenuse, which is the length of r. So that's z divided by the square root of x squared plus y squared plus z squared. And finally, phi is the same, the tangent inverse of phi over x. Okay. So in matrix form, this is your conversion between your Cartesian to cylindrical. This is your Cartesian component, sorry, cylindrical components. These are your Cartesian components. If you multiply this matrix to your uh, Cartesian component vectors, sorry, Cartesian components, you'll get cylindrical components, and vice versa. So just a fact, if you multiply this matrix to this matrix, you'll get the identity matrix 1, 1, 1, and all these are 0. Okay? Okay. So for spherical, these are the matrices. So again, if you multiply this matrix to this matrix, you'll get the same result as this one. Okay. So this is the end of the part 2 of your vector analysis lecture video. So the next part will also be recorded, and it will be about the differential elements, or the differential elements of your coordinate systems. So just a sneak peek. Yeah, there you go. This is your Cartesian differential element, which defines the length of a vector. Okay, so um, I'll just upload it there. If you have any questions, just feel free to post in the Uvle forum. Okay, I'll see you in next meeting.